Hello everyone. In this video, we'll talk about how to monitor the results of a nonlinear simulation as the model is solving. This can come in very handy in identifying potential issues with the setup and resolve them before it finishes to solve, especially when the model can take a long time to run. Let's see how this is done. Some nonlinear structural models can be time-consuming and challenging to solve. Therefore, monitoring their status and understanding how to diagnose potential issues such as rigid body motion during the solution is critical in identifying issues as early as possible. Doing this can save us a lot of time. Rigid body motion may occur in an analysis when contact goes undetected or when the user defines any boundary conditions incorrectly. When this happens, a simulation may either fail to converge or it may proceed to solve a physical problem that is different from our model objective. It's important to note that there are two ways of monitoring nonlinear solutions: monitoring the convergence behavior and tracking the converged results. The former allows us to check the convergence pattern to see if the solution is progressing smoothly or not. The latter gives us insight regarding the actual intermediate answers up to that point. Several real-time solution response graphs such as force, displacement and other convergence plots, solver output file and various other items help us monitor the status of convergence, which can be helpful in monitoring the convergence pattern of solution. Instead, we'll focus our attention on reviewing intermediate results through the use of Result Tracker. This helps us view specific results such as stresses, strains, displacements, and contact results for substeps that have converged, so they are actual valid solutions. They help us in identifying potential issues with the model instead of having to wait after the entire solution has completed. In ANSYS Mechanical, the Result Tracker feature is available for the structural, thermal, and explicit analysis. Depending on the type of analysis, relevant result trackers are available for monitoring. In this video, we will demonstrate this feature on a static structural analysis. While many result trackers are available for structural analysis, in this video we'll use Deformation Result Plot Tracker and Contact Results Tracker since they are commonly used for diagnostic purposes. The Deformation Result Plot Tracker enables to plot the total deformation for the solution available so far, so we can verify if the model is behaving as expected. Contact Results Tracker is used for monitoring various contact outputs specific to a given contact pair. Using this, one can monitor any changes in the contact status, loss of contact, or changes in other contact-specific quantities such as stiffness, gaps, penetration, etc. Let's go ahead and show how result trackers can be used in a simple nonlinear example to identify the problems in the model early in the solution process. This model consists of a rigid indenter and a rigid base and an elastomer sample modeled using hyperelastic material model. The objective of the simulation is to study how the sample deforms due to indentation. Due to the symmetry in geometry and the load, this model is suitable for a 2D axisymmetric analysis. But for demonstration purpose, we have decided to model it as a 3D model with cyclic symmetry on a 30-degree sector. The indenter and the base are modeled as rigid bodies, assuming that we are not interested in the results for the rigid bodies. Frictionless contacts are used between the base and the elastomer, and indenter and the elastomer. Notice that contact side should always be on the flexible geometry. In this case, the contact side of the contact pairs is on the elastomer. A translational joint is scoped on the upper indenter face to allow indenter to move in the x direction only. A fixed joint scoped to the lower face of the base is used to fix the motion of the base in all directions. Let's go ahead and define a joint load. Right-click on static structural and insert a joint load and scope it to the translational joint. Change its type to joint displacement. Set the displacement to 2.5 mm so the indenter moves in the x direction by 2.5 mm. Under solution information, insert total deformation result tracker and scope it to all bodies. Next, insert contact tracker. Scope it to the frictionless contact between indenter and elastomer. Set type to number of contacting to monitor the number of elements that are contacting during the solution. Since indenter is going to be pushed down into the elastomer, we are expecting the number of contacting elements to increase during the solution. Go ahead and solve the model as set up. Notice that the results tracker can also be defined on the go, so the users need not interrupt a run if they forget to define them beforehand. Now click on the contact tracker to monitor number contacting during the solution. You can see that the number of contacting elements immediately dropped, indicating the loss of contact and possible rigid body motion. Right-click on total deformation tracker and hit update to see the total deformation of the elastomer so far. You can see that the elastomer is not constrained properly and it flew away. The use of result trackers allows us to see that there is a possible problem in the model before the entire solution completes, which can save us time. Let's go ahead and add symmetry boundary condition. Right-click on the model and insert symmetry. Scope symmetry to the side face of the elastomer. Select user-defined coordinate system. Set symmetry normal to the x-axis. Next, repeat the steps to insert new symmetry object. Scope the symmetry to the opposite side of the elastomer. Select global coordinate system. Set symmetry normal to z-axis. Now let's solve this model again. Click on the contact tracker to monitor number contacting during the solution. We can see that there are several elements in contact now, indicating that the contact is established and there may not be any rigid body motion. We can update the deformation plot tracker to confirm this behavior. However, around the time of 0.4 second, we notice that the number of contacting elements decreases significantly. Let's update the deformation tracker to see what may be causing this. We can see lots of penetration due to elements skipping over the fillet. This is because we did not include the full face of the indenter in our initial contact definition. We always expect in this model that the number of contacting elements should increase. So, if we have an idea of what to expect, result trackers can either reassure us that solution is progressing smoothly, or they may warn us when something unexpected is happening. So let's stop the solution and fix this. Deformation tracker is especially useful to give the snapshot of what is occurring right now. Let's adjust the model one more time. Under frictionless contact between indenter and elastomer, add extra surface for the target. Go ahead and hit solve. Click on the contact tracker. Although number contacting increases and then decreases a little, this amount is relatively small and number contacting doesn't decrease below the initial contact. Click on the deformation tracker. Deformation shows expected behavior. We don't have to rely only on one tracker to monitor the progress of the solution. Now, let's change the contact tracker to monitor penetration. In this case, the penetration seems reasonable, but if we wish to reduce it further, we may increase the contact stiffness, and such a decision can be made on the go by using contact tracker. Sometimes, the contact stiffness might be too high and may cause element distortion errors. In that case, we may reduce it for better convergence behavior. This way, one can use different result trackers to monitor the progress of solution and identify any necessary remedial changes on the go. This completes the demo. Now let's summarize this discussion. In this video, we showed you how to use result trackers to monitor the results during the solution process. These tools can help us save a lot of time while solving complex and computationally expensive models. Using result trackers provides several advantages, such as they help us in identifying any incorrect model setup without having to wait for the model to finish running. This can save us time, especially while solving time-taking models. They help us in monitoring solution progressing without stopping the solution. Using contact trackers, one can identify any rigid body motion that may be caused due to loss of contact. This concludes the video. We hope that this video was helpful. Give the result trackers a try the next time you're solving any complex nonlinear models in ANSYS Mechanical to monitor the solution progress. If you did find this useful, then please like this video, share it with your peers, and do subscribe to our channel. You may also visit ansys.com/courses to discover more useful courses.